Morning, everybody. We're going to go to the next section today, and we'll do part of it today. And actually, we're going to have, I think, 4 days on this section, 12.2. So for 12.2, we'll talk today about heat of fusion and heat of vaporization. So when you hear the word fusion, you think of things coming together. But heat of fusion would be the energy required to melt a solid into a liquid. So I'll define that for you. So amount of energy needed to melt 1 kilogram of a substance into a liquid. And in your book on page 324, you'll see a chart of heat of fusions of different substances. So for example, ice. Write that down for you. So for ice, it's 334,000 joules per kilogram. And so that tells you the energy you need to melt 1 kilogram of ice into water. For lead, it's 20,000 joules per kilogram. So that gives you an idea of how much energy there is in the water. It's 10 times, more than 10 times greater to melt ice as it is to melt lead. Okay, so we can use this. Actually, before we go on to that, let's do something else. So that's heat of fusion.
Wait, so Miss Holly.
Yes.
So it's easier to melt ice than lead?
That's a good question.
I'm sorry, vice versa. It's easier to melt lead than ice? That's crazy.
It is, so that's a good question to bring up because it would be at its boiling point. So if you are already at the boiling point of lead, then it would be a lot easier, sorry, not the boiling point, the melting point of lead. It would be easier to melt lead at its melting point than ice at its melting point. So lead's melting point is what? Maybe like 3,000 degrees. So if you were at 3,000 degrees, the energy required to then make it go from solid to liquid is a lot less than if you were at, say, 32 degrees for ice and having it go from solid to liquid. So now heating it up, though, you need to heat up lead to a high temperature. So that's a lot of energy. But once you're at that temperature, the energy required to then make it go from solid to liquid is a lot less.
Okay.
There's two kinds of energies you have to think about. There's heat energy, to make it get hotter, but there's also energy to make it go from solid to liquid.
Okay, that makes more sense. I was like, that's crazy.
Yeah, but that's a good point to bring up because, that doesn't seem to make any sense because, you need to have 3,000 degrees for lead to melt compared to ice at 32 degrees. And so that is a lot more energy to make it go from, say, room temperature to 3,000 degrees. But when you're at that temperature, then it's easier to make it go from solid to liquid.
Right, okay.
Yeah, I'm glad you brought that up because that is, because it doesn't seem to make any sense, but hopefully that cleared it up. Okay, so that's heat of fusion. And heat of vaporization would be going from a liquid to a gas. So vaporizing something means to have it go from liquid to gas. So it's energy required to vaporize a liquid, 1 kilogram of a liquid. And again, that would be going from liquid to gas. Okay, and also on page 324, you'll see heat of vaporization in that same chart. If you look up water, it's 2,260,000. joules per kilogram. And then if you look up lead, that's 864,000 joules per kilogram. So there's two things to look at here. Compare water's heat of vaporization to ice's heat of fusion. And you can see it's a lot more energy required to make the liquid go into gas than a solid go to liquid. So it's 2 million compared to 330,000. And that's because the molecules, as they go from solid to liquid, they don't really change their movement a whole lot. You know, they're going from being in one place and vibrating to then flowing through a substance. And that's not a huge change in their movement. But going from liquid to gas is a big change in movement because they're going from staying in one place to then jumping out of the container and bouncing around at about 1,000 miles per hour. So the energy required to make it go from liquid to gas is a lot greater than going from solid to liquid. And you can compare again, lead is a lot smaller than water, but lead still has a much greater heat of vaporization than it does for heat of fusion for the same reason. And so this would be at the boiling point. You know, for water 212 degrees Fahrenheit, when you're at the boiling point, the needed energy to then go from that boiling point liquid to having it as a gas is 2,260,000 joules per kilogram of substance. And then for lead, it'd be the same thing. At its boiling point, which would probably be like 5,000 degrees, the energy required to make it go from liquid to gas would then be 864,000 joules per kilogram. I should have already written this down, but I'll go back for a second. You're going to see in your book H of F for heat of fusion, or you might see it as H of F US, just depends on how your book writes it. And then you're going to see it as H of V or H of VAP for heat of vaporization. Okay, so the equations to use for this, for the first one, heat required to melt a solid, depends upon two things. So energy is Q, or heat. So we can think of Q as the energy or the heat. And that equals the mass that we're melting times heat of fusion. And then heat required to boil something or vaporize, either way. Heat required to vaporize a substance is a similar equation. You take the mass of the substance and multiply it by heat of vaporization. So it's mass times heat of vaporization. So let's go through an example using these equations in your book on page 325. It says, suppose you're camping in the mountains. You need to melt 1.5 kilograms of snow at 0 degrees Celsius and heat it to 70 degrees Celsius to make hot cocoa. How much heat will be needed? So we have to look at Q, that's what heat is. And we're going to have to use both equations. Actually, I'm sorry, one equation. So let's go ahead and clear this off. So we start at 0 degrees Celsius. And what we need to do, and it's ice right now or snow. We have to first melt it and turn it into liquid. So when you melt a substance, it will still stay at 0 degrees Celsius at the beginning. So the energy required to melt a substance goes into making it go from liquid or from solid to liquid with no change in temperature. So that would be heat of fusion. The energy required to make it go from solid to liquid with no change in temperature. After that, you then make it go from 0 degrees Celsius to 70 degrees Celsius. So there's going to be two changes here. there's going to be a phase change going from a solid to a liquid, and then there's going to be a temperature change. So we'll be using two equations. For the first part, when you go from solid to liquid, we'll use the heat of fusion equation, which says this, that Q equals mass times heat of fusion. The mass of the snow, we were told it's 1.5 kilograms. And then times heat of fusion, we're looking at ice. So you go to page 324, look it up on the chart, and we can see that's 334,000 joules over kilograms. So the units will cancel out with kilograms, multiply that, and we get the energy required to melt the ice. And that's going to be 501,000 joules. Okay, so that's the first step we did right there. Then we have to go into this next step right here and account for the temperature change, which we'll be using Q equals MCAT for. So if there's a temperature change, we use the MCAT equation. If there's a phase change, we use this equation. So the mass of the ice, 1.5 kilograms. We put in C, so this is water. So it's going to be 4180 joules over, actually, sorry, that's kilojoules over kilograms times Kelvin. And then the temperature change, we're going from 0 to 70, so it's 70 minus 0. Multiply that out. Oh, I got that reversed, I'm sorry, that should be joules, not kilojoules. Okay, so multiply that out and we'll get the heat required to make it go from 0 to 70 degrees Celsius. And we get for that 439 kilojoules. The last step would be to add these two together. Now they're not the same unit though, so we have to convert them either both to joules or both to kilojoules. I don't know if they ask, no, they don't say which one you need to do, so we can do either. I'll just make this into joules. So multiply it by 1,000. There are 1,000 joules in 1 kilojoule. And that will convert it into joules. So that would give us 439,000 joules plus the 501,000 joules. And that would give us an answer of 940 joules. So the total Q would be 940,000 joules. Any questions about that? So they don't specify, you can either put it in joules or kilojoules at the end. It doesn't matter unless they tell you to put it in a certain unit. Just make sure that you do have the right units, because the MCAT equation will give you kilojoules, and the other equation, the Q equals heat of fusion, will give you joules.
Ms. Holly?
Yep.
So why do we need two equations? Is it because the temperature change and the phase change are separate?
Exactly, yeah, so there's two kinds of things happening. And so you have first the phase change, energy required to melt something, where you have a change in the phase, you go from solid to liquid with no change in temperature. Then there's other energies you have to add to a substance to make it go from 0 degrees Celsius to 70 degrees Celsius. So we use two different equations to account for both the phase change and temperature change. Okay, if we're looking at something that's going from, let's say ice to steam. So we would be looking at first going from ice to water. And ice at 0 degrees Celsius to water at 0 degrees Celsius. So we would be using Q equals M times heat of fusion for that one. Then we're going from water at 0 degrees Celsius to water at 100 degrees Celsius. That's the boiling point of water. So there's a temperature change here, so we use Q equals MCAT for that. And then at boiling point, water will then turn into steam. And it will stay at 100 degrees Celsius as it turns into steam. And so then we would use Q equals M times heat of vaporization for that. Now let's say instead we had ice at 30 degrees below 0 Celsius, and they're asking the same thing, ice going to steam. So for this one, what we need to do is have ice first go to its melting point at 0 degrees Celsius. So it's still ice at this point. We'd have to use Q equals MCAT for the temperature change. Then ice will go to water at 0 degrees Celsius. We would use Q equals M times heat of fusion for that one. And then water at 0 to water at 100 degrees Celsius. We'll use Q equals MCAT for the temperature change. And then water going to steam, be the last step. And for that one, we would use Q equals M times heat of vaporization. So there can be a lot of steps in these problems, depends upon all the phase changes, temperature changes you do. But for every phase change, you use either M times heat of fusion or heat of vaporization. And then for a temperature change, you use Q equals MCAT. And then you'd add up all of these Q's together to get the total heat needed to change the substance. Any questions about that? Okay, on page 325, do 19 and 21 for today. I'll write on here too. Questions 19 and 21. And then there will be a quiz tomorrow. It'll be over Monday and Tuesday, so it won't be over today. So it'll be over your notes, vocabulary words, and then your homework problems from yesterday and Monday.
So Miss Holly.
Yes, go ahead.
So for number 19, it's basically just going through one phase shift. Is it going through a temperature change?
Yes, it is. Yeah,
Okay.
For that one, right on here too. So you have ice at negative 20 degrees Celsius, and it's going to water. So yes, there would be both a temperature change. Ice goes from 20 degrees below 0 to 0 degrees Celsius.
Right. Yeah.
So it's still ice, and then it has to go from ice to water at 0 degrees Celsius. So yeah, you have both a temperature change and also a phase change.
Okay. Thank you.